All right. So second to last chapter, chapter 11 is about stream processing. I thought this was an interesting chapter perhaps I shouldn't have been surprised, but given this book, this author, it was more conceptual about sort of the abstractions and the uses and not as much really about like how you actually go about doing stream processing. So again, in hindsight, perhaps I shouldn't have been surprised. But so this chapter is mainly these three pieces. So it introduced what is stream processing. So you're dealing with data that's rather a fixed size, like just a file. You know how big it is, whether it's small or big. You know it's this long and it has an end. Where you have continuous data that might just be constantly coming in. And so even though you can do batch processing somewhat frequently, maybe if you're lucky, you can run it hourly. There are use cases where people want stuff every minute or even less than that. They only want a few seconds delay. And so that's where stream processing comes in. So we talk about those high level things. We get into sort of like how databases and other systems have been able to sort of take advantage of the advances in streaming. And then finally, the third part of the chapter talks about like how things actually, a little bit, not super deep, a little bit about how things actually work inside stream processing. So that's what we're going to talk about today. I've sort of taken notes at a little bit of a higher level, so feel free to stop if you have questions or I think it doesn't make sense, or if you want to kind of go through the examples a little bit deeper, because I'm just sort of going through and touching on the higher level concepts here. So the first thing that we talk about is that streaming is really the idea of you're pushing information, right? So instead of pushing, you could be pulling, and you could do polling. But obviously, once you get to higher frequencies, polling gets really expensive. And so, if you were polling every second or even sub-second, I mean, and if you have multiple people all polling, every second, that just gets super expensive. So you need a better way to handle this. And so the idea is you have to have the push side actually handling things. So generally speaking, and to me this seems pretty intuitive, but again, stop me if I'm going too fast. But so I think everybody's at this point pretty much heard of streaming, and so the idea is that you have a stream, or sometimes it's called a topic, and so this is basically one contiguous group of information. And obviously, if you look at like Kinesis, Kafka, whatever, they've got many streams, many topics going simultaneously. So the abstraction is that you have this publish subscribe model, all right? And you can have producers and consumers. And the simple case is you have one producer that's queuing up events on one end, and you've got a consumer that's pulling off events at the other end. But the reality is you can actually have multiple producers, and you can have multiple consumers, and you can do it in any combination, multiple to single or multiple to multiple. So there's two things that we can ask when we look at a streaming system to sort of differentiate the different kinds of implementations. So the first question we can ask is, what are we going to do if the consumers aren't processing things as fast as the producers are creating things? All right, you're gonna build up a backlog of events. And so your options are, you can drop the extra ones, which of course is lossy. You can buffer them, in which case you're taking care of that problem, but eventually you do need to do something about this consumer to speed it up, or else it's going to lose messages eventually at some point. And then not so much in modern streaming systems, but there is the idea of applying back pressure, where basically you say, stop producing them so fast. And then the second question you can ask is, what kind of system is this? Is this a system where if nodes go down, things can be lost? Or are we trying to, again, provide a nice abstraction where fault tolerance is provided for you by this underlying system? And so generally speaking, when you look at modern streaming systems, why people use them, if they didn't care about about lost messages, if they don't care about drops and they don't care about nodes going down, you don't need a modern streaming system. So why people generally use message brokers is because they want that functionality to be provided, that there's buffering so you don't lose stuff, and that there's fault tolerance so that you don't lose stuff. So then gets into different ways you can actually implement this. So one way is you can do direct messaging. And the author mentions this, and this is not something we're really going to talk about. So you have different options at the network layer. If you're familiar with what these things are, there's UDP, there's UDP multicast, there's a version of IP multicast, and you can even do things like web calls or RPC calls. And that's one way to communicate between typically a single producer, single consumer. But again, you're not getting the fault tolerance and these other kinds of things. And so if it's something very simple, very lightweight, applications can use this. If Netflix is streaming stuff to you, I don't even know exactly what technology Netflix uses today, but it's probably some version of that. If you're watching a movie and a certain packet gets lost, it's going to get lost, and then you're just going to keep watching. It's not worth the trouble to go and figure out how to pause, resend, make sure you get every single last packet. You, the user running the application, if you really care about that little glitch in your video stream, you need to hit the rewind button, and then it'll go back and it'll resend stuff from that particular point in time. So mostly what we're going to talk about in this chapter is message brokers. And so this is where you have a separate system. You have a separate server that's running the message broker system, and the producers and the consumers are clients as far as this system is concerned. So the message broker typically is going to use some form of queuing, like we've talked about, where the consumers stick stuff in the queue. But fundamentally, that means that because it's not this synchronous direct event where you're connecting producers and consumers, it means it's asynchronous. And it means that the producers don't know when they send a message, when or any specifics about how those messages got consumed or when they got consumed. So I don't think it's really covered in the book, but just in terms of a way that people handle this is that you can then have another stream that's return messages that notify the producer what happened, some type of acknowledgments or whatever. So if necessary, you can do that, and that's a simple way to give sort of the same. You can have something that looks like synchronous, where basically the producer sends a message and it waits until on its other stream it gets an acknowledgement that it was received and processed. So when you set up a streaming system, if you have multiple consumers, there's usually two different reasons why you have multiple consumers. One is you're doing load balancing, so you're divvying up the work to multiple consumers. The other thing that you can do is you can have multiple systems that just want to subscribe to the same information for different reasons, and they're all independently doing their own thing. And you can obviously have combinations of both of these. So you can have independent consumers, and any one or more of them can be load balanced, and that's fine. And then the final note here in this sort of first section of the chapter is that you have to understand that once you start doing this business of queuing things up, and if you have multiple partitions and load balancing, that at the end of the day, your messages are not guaranteed to be processed in the same order that they were created. And so for most workloads, this is not an issue. But if you have a very specific workload where it must be, then you really have to be careful, and you have to think about, you can't necessarily just willy-nilly set up something like Kafka, partition it, have multiple load balanced consumers, and because if you do that, then you're not necessarily guaranteeing that with those multiple consumers, they will be processing things in the same order that the events were generated. All right, so that's the first section here, just sort of setting up the scene for what is streaming, this concept that you've got topics, you've got producers, you've got consumers. Um, any questions, comments, thoughts at this point? Okay. Let me just take a quick peek here, see if I can, nope. All right, Brian, you just need to, I try, but it's so hard to get my chat window to work when I'm sharing, so people are
There
just,
was
There's nothing in the chat.
Yeah.
Type, it's
okay.
fine.
All right, and it's fine. You guys should feel free to chatter away. I just don't want to miss a question if somebody actually wants to talk about something.
Stephen was mentioning the tools that Netflix uses.
Cool. Yeah, Netflix is a very interesting company. All right. Okay, so the next we're going to talk about implementing this idea of message passing with partition logs. And if you have a log-based message broker, then really you kind of potentially get the benefit of both worlds. You get this fairly lightweight message delivery, where it's really fast, potentially, if you implement it right. But at the same time, you can have this good permanent storage. And it's a lot like the log-based databases we talked about. So you have this log-based storage. And I specifically mention here, Kafka, which I'm a little bit familiar with, Amazon Kinesis. These really popular products use this technology. And so it allows them to give you a very rich feature set. We'll talk a little bit more about the features, but the idea is that you can have this really high speed, really good scalability, and yet you get all these other properties from having this reliable storage and the ability to actually go back in time and replay messages and stuff like that. So when you have these structures, then the producers, what they're doing is they're just doing append only to these logs. So this is just like the log databases we talked about earlier. And the consumers are reading from the log sequentially. And depending on the specific product, basically when you get to the end, you've processed everything. And so typically you don't want to be polling, you actually want to be notified when there's more data. And then you, again, start reading from the log where you left off until you hit the end. Scalability is usually done by partitioning the log. You can also have replication for fault tolerance. And so usually when you do load balancing in this architecture, what that means is if you have 5 partitions, then you can have up to 5 consumers that are each monitoring their own separate independent partition, and they don't get in each other's way, and things are really fine. And so you have to be a little bit careful because there's a little bit of a limitation in that the number of partitions is sort of a limit on the number of consumers you can have. And the book does talk about if you had a system where you were using message passing, but instead of really lightweight messages, you had a queue with not as many messages, and each one took a long time to process. Let's say it took, 2 minutes to process each message. Well, then you probably wouldn't want to do this partition business. You probably want to have a single queue and multiple consumers pulling off of that, since each one is going to take a really long time to process. There's an optimization you can do if you have these log-based systems where the consumers, they don't need to send acknowledgments anymore, because even if something happens to them and they say lose connectivity for a short period of time or something like that, they are guaranteed to always process the messages that they see in their partition or partitions. They're always guaranteed to process them in order. So really all you need to know is one number. You just need to know the offset of what's the last message they successfully processed. And if there's the possibility the node will completely fail and then you need to assign the work to a new consumer, then you just need to periodically make sure that you know what the offset is for each consumer. So that's a lot less work than constantly having consumers send acknowledgements back to the broker. And so again, so this is something else that even though you're using disk here, this is a way in which log-based message brokers can be very efficient, can be very fast. Of course, one of the downsides is that because you're writing everything to disk, you now have to worry about disk space. So a lot of these systems ultimately have some configuration that says this is the maximum amount of information we can hold on a specific topic. And so oftentimes they will use a circular buffer, if you know what that is. And so if you actually exceed that, then basically you are going to lose messages, the oldest messages, off the back end. And so you can consider this a good thing or a bad thing, depending on your perspective. But basically, this means that while the concept of not losing messages is there for very short-term failures, if you have a consumer that really can't keep up with a particular stream, then eventually what's going to happen is it's not going to keep up, and old messages are going to start to be deleted, and then the consumer's not going to get all of them. And so this is actually potentially a side benefit, because let's say you were doing development, and so your production system, the consumer's obviously going to be reading everything, process everything. Well, you can just shut off your test server or your development server from where it's subscribing to a particular stream, and it means it's going to lose messages, but you don't care because it's not a production system. And so the message broker doesn't have to worry about this ever-growing buffer of messages that it's trying to keep up for each consumer. It just knows that if I don't hear from you in a really long time, then you're just going to fall behind. Tough luck. And at least the broker's not worried about trying to save all that information. And then I mentioned this before, but so then the really nice thing about this is that as long as you're not exceeding this maximum allocation that you have for a particular topic, you can arbitrarily go back in time whenever you feel like it. So if you want to reprocess yesterday's messages, if you know what the first message is from yesterday, then you just set your offset back to that, and then you just go and you replay all the messages for yesterday. So this is very convenient. The author talks about you can kind of debug things this way. You can, there's lots of things that you could do. It also means that if you have a brand new system, so if you currently have a topic, it's got two consumers, and then you decide, oh, there's this third way that we want to use this information. They don't have to just start from now. They can actually go and they can pick a convenient starting point. They can go back to that time, and they can then build up a history. So it's really nice if you have a new system. Let's say you have some dashboard, and instead of it just starting out blank, if you could say, oh, well, I started with all the data in the last week, then if you have something like a 7-day moving average on some statistic or something like that, boom, you're able to have that from day one. So things like that. All right. Any comments, questions about partition log message brokers? All right. So then it was interesting. So the chapter takes a little bit turn, and it says, rather than talking about sort of streaming and how you're passing information from one system to the other, let's talk about how a database might want to sort of steal some of this technology. What are some of the things that a database might want to use it for? And so eventually this kind of abstracts into how different systems can, rather than thinking of streaming as sort of like this high level thing that I, as an admin or as an application developer, are moving information from one place to another, like, imagine like a stockbroker watching a stream of like, stock prices or something like that. Now it's kind of looking like under the hood. Hey, you actually might want to use these nice streaming semantics for implementing different things in your system. So basically the author says, hey, a replication log for a database Sure looks a lot like a stream of writes. And so what if we thought of it that way? How can we use this to help build heterogeneous systems? So a very simple thing is you can keep different systems in sync. So you might have your OLTP system where you're doing, you know, your quick short interactions. You might have a data warehouse. Now, yes, traditionally you might have ETL, systems that maybe run nightly. But another thing you can do is you use streaming in order to more incrementally, continuously keep that data warehouse updated. But it's not just a data warehouse. You might have a certain kind of search index. You might have a recommendation system. You might just have different ways that you want to view this same information. And it's great. You can have multiple copies that are each optimized for different types of access. And you keep them all in sync just by streaming the information from one to the other. So if you think about, actually, I got ahead of myself a little bit. So if you first try to implement this just by having this done at the application level, and you have clients doing dual writes to multiple places, what you quickly will see is that you can get into race conditions. So all the weird stuff we talked before about where one message is faster, another message is slower. And then if you two different clients try writing to the same particular key, then you can get into all these race conditions. And so ultimately sticking a message broker in the middle helps you solve a lot of these problems. So there's a couple different ways you can implement this. So one idea is change data capture. So change data capture, it's a low-level way of keeping this log. So basically it's by key, by primary key, you're keeping track of things. And so you're just keeping a log of everything that happens to the record. So if you have a fairly large record and just one field inside of it changes, generally speaking, what you're going to do is in change data capture, you're going to send that whole record. Okay. And you're just gonna keep an ongoing log of all the changes to any records. And so it's very easy then when you have any change, if you have this nice stream semantics, to then just simply say, I'm going to subscribe to this stream, and then I'm going to get in order, I'm going to get everything that happens, and I'm going to be able to then sort of replay that. And I can build a very different data structure for the same actual information. So the author talks about that if you do this, basically what you can think about this is you can think about it as single leader replication. So now the primary database acts as the single leader, and then all the people who are getting these streams, basically, they're acting as followers. But again, this is now heterogeneous systems as opposed to when we talked about, single leader replication. Normally we're talking about within a given database, just simply trying to serve requests. Now we have the idea you can have your main database that's doing that thing, but again, you can have your data warehouse, you can have your full text search, you can have, whatever, all these other systems that are using this information, but externally through change data capture. A few other fine details if you're gonna do this. If you need to bring up a new system, generally speaking, you don't want to replay every message from the beginning of time. And so typically you're going to want to say, here's a snapshot, and then I only have to process a shorter amount of events since that snapshot. I don't know if this has changed since the printing of the book. At the time of the printing of the book, the author said that some systems support this, but sometimes you just have to manually do your own snapshot and say, hey, I have a snapshot that's from 8 p.m. yesterday. Now let's replay all the messages since 8 p.m. You have to kind of manually set that up. I don't do this every day. I don't know if anybody knows. I would assume that support for this would tend to be better today, where it's sort of built in. You can say, give me the most recent snapshot and play the messages since then and not have to like manually do all that.
I want to say it depends on the system, but like for Kafka, it has something that has compacted frames where it will still stream you everything that it's gotten, but if there's things that have the same key, the same kind of index lookup, it will only keep the most recent copy of that. And so that's what I was just thinking. Kafka does that. I'm blanking on anything else that would do like other systems I've seen, you know, you can get snapshots since a certain time. But I'm thinking those are more lower level, like, you know, storage, like ZFS or something.
Cool, thanks. I can remember like 20 years ago, I was replicating just regular old SQL databases. And at that time, Microsoft SQL Server was so fragile that even though it had built-in support for doing a snapshot, sending it, restoring that snapshot, and then, you know, replaying the logs since that, it was so fragile that if like anything happened, then it would just blow up in your face. And so for us, it was actually easier to manually do the snapshot, manually copy it to the file system on the other box, manually load it up, and then to say, okay, I've loaded up this snapshot, now start replicating from that particular moment in time. So I don't know. Yeah, I think it probably just depends on the system and the level of support. And then another note here at the end of this section is that log compaction is going to be really important for keeping down the size. If you're going to be persisting everything, and you need to be careful to make sure that your log compaction is actually going to be able to keep up. So you may be scaling things up on your message passing system, but you better make sure that your log compaction also scales nicely with all the activity if your system's going to grow really big. All right, so that's change data capture. That's once again not something very tightly coupled like replication within a database, but sending stuff out to a different system. It could be a system that's you know, made by a completely different vendor, supporting a completely different sort of use case. And that's again at the very low level. So another way you can handle this same concept of I'm sending all my information out to another system is you can do event sourcing. So here, instead of low-level, record-level information, you talk about events. And so I think in the book, there's an example of, you know, customer X has canceled their subscription. So canceling their subscription could involve multiple things, some change to the profile, some change to the accounts table, changes to other tables. But the idea is that you've sort of atomically said, here is the key concept: user canceled subscription. And it helps you because then you sort of abstracted, you know, into, you know, we often talk about like in the whole stuff about like transactions and you know, multiple keys and, you know, all this stuff. You know, you get all this complexity between race conditions and whatnot. But if you can just think of this as one atomic event, then that really helps simplify things. So generally speaking, if you are going to be capturing this log of events, you want it to be append only. And so you can have things like a tombstone event or whatnot, but you still want it to be new events, new events. You don't want to literally go back in time and update or delete things the way you do in something like a SQL database. So you want these to be immutable actions that, again, just you can record more and more of them, but you don't want to have to go back and have to actually physically update anything. So one real difference, however, with event sourcing is, let's say you're talking about a user cancels their account, and maybe in the user profile there's just one column, there's one field that says, you know, is account active, and it changes from true to false. You're not actually storing a copy of the entire user profile record. You're just really capturing the fact that is active changed from true to false. So this means that if you want to know what is, Bob's user profile, you need to go back and you need to look at the entire log of everything to see what are all the changes to potentially all the different fields. You can't just use the most recent. So that's sort of a trade-off with doing things the event sourcing instead of the change data capture way. And so it means that you can't really do log compaction, and you can't really kind of do some of those optimizations. I don't know if anybody knows if they're familiar with if people are using event sourcing. I was not that familiar with this concept of higher level event sourcing, and it seems to me that it probably hasn't taken off. Anyone?
I'm not aware of it.
It's becoming a lot more active in the quote unquote serverless environments. So AWS Lambda has a lot of event sourced items, where like if you have a file that drops into S3, it'll send an event over to a Lambda function that fires off and does something in response to it. So I haven't seen it kind of built into a lot of data systems, but I have seen it as a general architectural item.
I see. Okay, I guess that makes sense. Something like that. Again, you want a sort of a more higher level concept of what's the event that happened. It's not really like a record level kind of a thing that you're talking about, right?
I mean, yeah, I guess the record level is kind of where like depends on the size of your record is what I'm tripping over. Because it's like in S3, it's like, oh, this file was uploaded. I guess technically that file is a record depending on your view of stuff. And I think Dynamo can do it on a row entry as well. But usually it's like it's usually not something. Well, I guess it is still generic, but size of record is really the question.
Yeah, I think you can definitely say there's gray areas where you can blur. What do you consider change data capture? What do you consider event sourcing? And what do you just consider a generic message queue, right? A message queue is telling you about certain events that are happening. So I don't know that we need to have super bright lines, but like this is not my world, but I haven't really seen stuff where people are like what we're talking about, like, oh, user has changed their password, oh, user has canceled their subscription, where you sort of have those types of things being queued up, whereas just log based message broker, that's like every day you hear about people using that abstraction.
I mean, I guess it's one of those, I see event sourcing more as kind of an abstract pattern. And then to your point of like, does it come over as, say an individual, like you have a database and how the database is doing its synchronization, it's, fellow, it's high availability synchronization, whatnot, versus is this something that happens as part of a larger, commerce scheme, like if you cancel a subscription, what does that mean to all of your entitlements and everything, like those kind of pictures. But there's an event that happens and then it gets dumped onto some transport, maybe a message bus or whatnot, like all of them. It really is about the concept of event happened. The event has some, to your point, business meaning, higher level value, and then what are all of the downstream actions that need to happen due to that?
Cool. Thanks, Chris. Okay, so I'm going to move on to the next section where the author talks about immutability. And immutability in general, in terms of like computer science, computer engineering, data processing, immutability is a topic that just comes up over and over again. I mean, you see this in programming languages. And so some languages have immutability, others do not. Some languages under the hood use immutability, even though to the user, it might seem like it. Well, so for example, specifically what I'm referring to is, I don't know exactly how Python works under the hood, but I know in R, all of the things that you think of as variables, as data frames, are actually immutable. So when you just say, x equals 2, and then you say x equals 5, in actuality, what you're getting is new memory allocated. Um, and that thing is 5. And eventually, the old memory that holds the 2 is still there, and it'll eventually get garbage collected. But it does not literally write the 5 over on the 2. So objects in R are immutable behind the scenes. So in this case, immutability is really one of the key things that allows for a lot of the performance optimizations in streaming technology. And so there's an analogy I thought was very good, just about, if you know anything about bookkeeping, how accountants do things is they have an append-only ledger. The general ledger is supposed to be immutable. Once you've added an entry, you're not supposed to ever change it. You can have a correction that says, oh, by the way, this thing that happened on January 15th, you said it was $10, it was actually $9. That's completely legit to have a correction entry, but you can't literally just go back up 500 entries and just erase the 10 and change it to a 9. So here's where I thought there was a very interesting idea that the author talked about, which is that if you have something like change data capture, so let's say you have your regular database, you have change data capture, and then you're replaying all the events in change data capture to create, let's say a read-only data warehouse, kind of a system. Basically, what you're doing by doing that is you're creating an explicit process for translating, understand, implementing what to do when you get this log of changes. And so what you've done is you've really clearly defined the interface that says, when you see blah-de-blah events happening, then this is what you do when you're going to write it to your data warehouse or whatever. And by having this be explicit, instead of potentially intertwined and implicit and dependent on certain guarantees that your system is providing and blah, 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 so when you're just simply within one system saying, oh, I'm just going to pull information from here to there, there's a lot of assumptions around that information that you may have. But in this way, you may be very explicit. You can have very few assumptions about it, because it's just explicitly, here is this message queue, I'm pulling off of it, and this is how I'm going to process whenever I see a message that looks like an insert. This is what I'm going to do when I see a message that looks like an update, blah, 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 blah. So by having that all explicit, it really helps clean up sort of the definition of how these heterogeneous systems are related to each other. And so the example he gives is that if you decide you want to have some new functionality, it's really easy to just simply say, rather than doing an upgrade against this old system, I'm just going to create a second consumer, and I'm going to have the new version consume, do all of its stuff. I can run the two of them in parallel. I can compare them. I can do all this stuff. I can have very clean semantics. And then at some point when I'm very happy with the new system, then I can just turn off the old system. So I thought that was a really great way of, how do I want to say it? Of showing the power of encapsulating, all this change information into a very explicit stream and explicit rules on how you process that stream. So I would say for me, that's like a nice takeaway in terms of how, at the end of the day, streaming isn't necessarily new, but by having these building blocks, it's really made people who are building, new applications, it's kind of made their life a lot simpler. And then there's also a little section in there where he talks about concurrency control. And so it is possible to read your own data after write and see it and get a stale read. Talks about a little bit ways you can try to mitigate this, but that this is ultimately a problem. So, you know, depending on the use case, if I write to a database and I immediately try and do a read off of the data warehouse, I'm probably not going to be that freaked out that that thing that I wrote 1 second ago hasn't appeared in the data warehouse yet. You know, there's an expectation, but there's other times where it's not as so if it's like, you know, recommendation or something, you know, you kind of expect it to be more real time. So that's a potential issue. And then finally, in terms of limitations, I didn't feel like the limitations were that severe. But basically, you know, he said, if you have lots of updates and deletes, inserts are, you know, not so scary, but if you have lots of updates and deletes, then it can be really hard. And then again, what I mentioned, your garbage collection, you know, your compaction routines, it may be critical that they keep up in order to have your system perform well. And then another thing that I hadn't even thought about is something that could throw a real wrench into your system is if you have just some weird, rare use case that requires actual deletion. And so we were talking about healthcare a little bit at the beginning before we started on the book. And yeah, absolutely, healthcare has a lot of special rules. And so if there's a privacy rule that says you must delete this information because, you know, the patient closed their account, well, then you got to figure out how am I actually going to support that if my system is immutable and doesn't actually allow physical deletes. All right, so that was sort of the second section of the chapter where we're talking about heterogeneous systems and ways that streaming can be used. Again, not really at the application level, but more at sort of that data engineer level. And then the last part of the chapter talks about stream processing. So any other thoughts, comments, questions? Okay, cool. All right, so stream processing, which just naively, again, this is what I was really thinking of when I, you know, first got the book and I flipped through and saw what the different chapters were. The author talks about, hey, you know, when you have streams, basically what you can do is you can do some type of analytics, and you can take streams, you can process single streams, you can combine multiple streams and create new output streams. Ultimately, you're probably going to alert a user, display something on the screen, do something, you know, but in the meantime, you often have this stream processing that's happening at, with intermediate steps. And that's what this last chunk of the chapter is about. So a lot of the underlying just sort of basic mathy type stuff, mapping, filtering, partitioning of work, just so you know, that works exactly the same for batch processing. Well, I shouldn't say exactly the same. It works pretty much the same as it does in batch processing. So there's not a lot that needs to be said about it. What I can comment on is having used Spark, basically the way Spark does batch processing and the way Spark does streams using micro batching. Basically, that's how they handle the idea of bounded data or continuous data. But otherwise, just like the author's saying, everything else, the way it does mapping, reducing, partitioning, shuffling, all that is identical after the fact. So indeed, you know, really those underlying aspects don't change just because you're doing streaming instead of big batches. So we talked about some different uses. So this idea of complex event processing. So typically that's where, rather than looking at individual messages, you're looking for a sequence of multiple messages, different kinds of things. And I thought it was kind of this cool idea that whereas normally you think of a database as like, hey, you have this data that's relatively fixed. I know it changes, but it's relatively fixed, and queries come and go, and you basically, you match up the query with the data that the user wants, and you send that, data back, and then that query's gone. Obviously, sometimes query gets run over and over again at different times, but that's sort of the conceptual way of thinking about it. And here it's really the opposite, is you have, some search criteria, some query criteria that stays relatively permanent. And then the streaming data goes by and you match it, and the data comes and goes. And anytime you have a match, then you spit out a match. So I thought that was kind of cool to show that it's sort of like this reversal of the roles of data and query. And then talks about stream analytics. And again, it can be a little bit gray what you consider to be one versus the other, but typically, now you're talking about, you're producing metrics. So if you're doing, the number of comments per minute, that's not an end goal in and of itself. That's just another stream of information you're producing, which is, let's say every minute or every 10 seconds, I'm going to refresh this metric, which is the number of comments per minute. And the author notes that there's a myth that he wants to dispel. So just because people use Bloom filters, probabilistic algorithms that are not exact, and they use them because they're much cheaper in terms of like memory and compute, and they're much faster, that doesn't mean that they're required. So there's nothing inherently less accurate about stream analytics. It's just people choose these algorithms for performance reasons. And if you wanted to, you can compute, the exact histogram of anything. You can compute the exact mean of anything. You can compute the exact median of anything. But it just means that it'll be a more expensive computation than if you use some of these other probabilistic algorithms. Another use case is maintaining a materialized view. And so just like other stuff that we've talked about, if you want to maintain a copy of something, you can just push streams across, and then another system can maintain the copy. And then simple search. So an example was like, you have news articles, fairly large chunks coming across, and you have certain topics of interest. So streaming would be useful for that. You can imagine stockbrokers streaming, financial data constantly. And then finally, you can do something that's sort of like, RPC type stuff with streams. And the cool thing is that if you're using a streaming product, it provides fault tolerance in a way that just something like an RPC call wouldn't. So if you're trying to do an RPC call and the client, or sorry, the server that you're making the call to is disconnected for a minute, then basically your call just flat out fails. Whereas if you insert streams in there, then basically the message broker is going to hold on to that message. In a minute, when the server becomes available again, it delivers the message, and then typically you're going to get a response delivered back to you on a separate stream. So time is important in all processing, but it becomes really painfully visible when you're doing streaming. And so typically what you see right away is people are doing windowing. So maybe you do a window of like, say, 1 minute of time. But we've got all the issues with clocks not being synchronized and things like that. And so there's a couple of examples in the book. It's important. It's easy to see that what matters isn't when I got this message or the current time right now when I'm processing it. What really matters is this concept of event time. So when did the event actually happen? So if you have weather stations that are sending data, you don't really care like what time it is now when I'm processing the data. You care what time was it when it sent the temperature and the wind speed and the humidity, all that. You care about event time. So that's pretty clear. And so generally speaking, when you have windows, you have some sort of timeout. So you have this concept of a high water mark. And once you exceed that timeout, then anything that comes after that is going to be a straggler. And while one option is that you could sort of reprocess and do a correction, that's pretty rare in my limited experience. So typically what's going to happen is you're just going to drop stragglers. You can keep track of the fact that that you had stragglers, but ultimately, typically the point of streaming systems is you want them to be very responsive, and so you don't have time to go back and redo and correct things. For me, it's fairly intuitive, but I just wanted to kind of emphasize a certain point that the author doesn't really talk about in this chapter. So let's say, excuse me, one second. Let's say you're processing information in 10-second windows, but you know that your weather data can have various kinds of network delays and things like that. And so let's use something extreme. So let's say you allow 5 minutes for the weather data to get to you. And so you're okay with the fact that, you know, your data might be 5 minutes old, but you really don't want to lose data. So you're setting a very high timeout. You set 5 minutes. Then even if you set your window to 10 seconds, what'll happen is your system will be outputting like a new metric. You know, what's the average temperature in San Diego, let's say. It can output a new average temperature in San Diego every 10 seconds. But that that data that's coming out every 10 seconds is still 5 minutes old. I think most people understand this concept, but it wasn't really explicitly mentioned in here in terms of how this timeout plays a role. So the longer your timeout, the higher your lag is going to be between the output and the input. But I just wanted to mention it because when you initially start, like if you start programming streams, you know, when I was doing stuff in Spark, at first it's a little bit confusing, sort of this idea that like, oh well, if I have very short windows, then my data should be like really current. Well, it doesn't have to be. You could process data every second, but if your timeout's 1 hour, then all of your data is still an hour old, even though you're spitting out updates every second. So just wanted to make sure it's clear that the update frequency and the lag are two independent variables that you could tune. All right, so then finally, when we talk about windows, there's a few different ways that that you can organize them. And so what they call tumbling windows, those are just adjacent things. So you can say, I'm going to do every minute. So from 1 o'clock to 101, 101 to 102, 102 to 103. So they're non-overlapping. They're adjacent chunks of time. You can do hopping windows, or you can have overlapping time slots. So a very simple thing is they're halfway overlapped, but you can overlap it in other ways. So you can have, I think the example in the book is a 5-minute long window, and you can have hops of 1 minute. And so if you were doing something like, say, again, average comments, it's okay if they're overlapping. So the same comment would contribute to 5 different windows of that metric, but that's okay. You're just reporting, you know, some sort of metric. But you can imagine if you had some other kind of metric that was more like, I don't know, you know, total sales, and if you were sort of, you know, loading these into some database, then you wouldn't necessarily want, you'd more likely want a tumbling window. You wouldn't want to be reporting the same information 5 times and then have to somehow like sort of deduplicate it, you know, where it's being received. Sliding window, it's a little bit like a tumbling window, but instead of having fixed predetermined slots where you say from 101 to 102, from 102 to 103, let's say you had a 1-minute window. So when you first fire up the system, you're like waiting for my first message. And if the first message comes in at 1:02 and 15 seconds, then you basically say, I'm going to wait 1 minute from when that first message. So that means that I'll wait till 1:03 and 15 seconds. And then once that time comes and you've processed that stuff, then you say, okay, waiting for another message. Let's say you don't get another message until 1:03 and 50 seconds. There's 35 seconds you do nothing. And then once that first message comes in and at 50 seconds after, then you say, okay, now I'm going to start a window and I'm going to have 1 minute from 1:03 and 50 seconds to 1:04 and 50 seconds. So that would be a sliding window. And then also there's this concept of session window. I don't know a lot about this. I know that you need it in the analytics to do a lot of kinds of metrics that people care about, but I'm not sure if that's something that you more manually implement, or if it's something that is very easy for you to get some of the stream analytics to just sort of automatically, magically do for you. But so if you basically say, hey, a session on, Facebook is when someone's clicking around, and a session ends if they go 30 minutes without doing any kind of clicking around. All right, so that session could last 10 seconds, or that session could last 3 hours, where they're just constantly clicking, where they may not be clicking, but they don't go more than 30 minutes between clicks until finally, at 3 hours, they stop. And again, just like with some of these other things, you're not going to know a session is over until 30 minutes after it actually ended. So you can only find out sort of after the fact that you have this inactivity. Any questions about the windows or any of that stuff?
I had a quick question. How reasonable is it to assume that the network delay is short when we're talking about trying to figure out the offset of the clocks, right? So you keep the three different clocks. It's when the event occurred, what time the sending device thinks it is, what time the receiving device thinks it is, and then and then they make the statement that you can, with fairly short network delays. How big an assumption is it that you have a short network delay?
Well, I don't know. I have not implemented this technique. So what I can tell you is that, let's say you've got a device and it's sending you weather data, okay? And for some reason, instead of February 27th, that device thinks it's January 1st, 1974, okay? At least if you use this technique, you can then sort of translate, right, everything
True.
into something that's
Agree.
roughly February 27th. Maybe not the exact time to the minute, but at least you're going to get it, kind of in the right ballpark, right? I suppose one of the things, what my brain goes to is, rather than just taking a single difference between the time when the message was sent and when you received it, you could actually average over the last few messages, and maybe you would get, or not average, but rather like the minimum.
Yep.
You know what I mean? So if you took the fastest that any message ever got to you, then that's a little better than taking just sort of the single message, in case that one happened to be delayed, let's say a full minute before you got it.
Okay.
But yeah, I don't know. Has anybody else actually implemented this algorithm? Again, this will just help you with just a completely wrong clock. It's off by years. At least instead of you having, normally, right, I would look at this and I would say, oh, I have weather data that's 1974, and we implemented this system, last year. So it's invalid to have any date prior to 2020. Normally, what you would have to do is you just have to toss that data and say it's bad data. At least this algorithm will turn it into something on February 27th. May not be, the super exact time. I don't know if that's better.
I'm curious if anybody else had experience with it, because I don't know how good or bad an assumption it is to say you've got a short network delay.
Yeah. All right. I guess nobody else has. But yeah, and then I mean, at least if it's like a weather sensor or something like that, you assume that it's not a malicious, right?
Right, right, yeah, yeah, yeah.
It's not what was it that we talked about, Byzantine faults in the other chapter, right?
Yeah,
So
yeah.
at least it's just like, well, this damn thing thinks, part of my language, this darn thing thinks that it's, January 1, 1974, but at least it's not doing it purposefully to pathologically mess with me. So with my whole thing about averaging, right? If you were evil, then you could purposefully just keep changing the date, and then my average would be way off,
True.
Or you could just lie. you could have the time that the event occurred, and instead, you could just lie about when you sent it. So no, this definitely does not handle those types of situations.
I'd say there's also cases. I hate sounding like a broken record, but it's situational, because if you're just looking at like a single device that is posting as fast as it can, as soon as it can, that's a strategy that works for that. That gives you an idea what's there. And then you're looking at probably on the order of, if you have more than like a minute, really you're talking, if you have more than, seconds of a difference, then you have to kind of assume that their clock is off, because you're not going to see that much network delay from a pure connection standpoint. Because at that point, most of the connection protocols give up and everything. But
Yeah.
It all depends, because it's like, if you're posting if you're saying, oh, I'm going to record like 100 events, and then I'm going to post at the end of those 100 events, well, then your entire strategy changes, because you're going to have events that are held for like 5 hours or something. And
Right.
so it gets a little, when we say, with sufficient or minimal network delay, like we think of the network, and it's like, well, the network's really when we interact with the network and what are the things in between, not just, oh, I made a network connection. And so it all kind of falls apart there.
Well, yeah, and that's what I was thinking, Chris. Like, if you are monitoring I don't know, temperature sensor, or somebody's vital statistics, and they happen to be in, I don't know, like Nigeria or somewhere, can you still say that, the network delay is going to be a couple of seconds at most, or, right? I mean,
if it's a straight network connection, yeah, you're really just talking on the order of seconds.
okay.
Because as most, like a lot of TCP communication and everything gives up, depending on the nature of it, like after like 15 seconds it'll give up, right?
There's the timeouts.
Yeah, so that's kind of like, you can kind of guarantee a little bit to that degree. But if you have these collection networks where there are services in between, and like holding and forwarding this stuff, then your numbers get very different.
That's true. Good point.
And just because it's cool, from the last couple of weeks, I should say, this is all strictly for terrestrial numbers. Interplanetary networking is a totally different ball for us.
Fair enough. So monitoring the Nigerian prince's vitals on Mars is a whole other discussion.
Yeah, if you're steering the Mars rover, you can't assume a few seconds. No, I think that's really amazing, though, Chris, that like if I'm communicating with somebody anywhere, in Nigeria, that I can really, expect just a few seconds delay. I mean, I know it would be kind of annoying for like, a video chat if it was a 10-second delay, but just the idea that, I mean, a few seconds, it's I don't know, kind of blows my mind how powerful the internet is.
Well, I agree. And if you think about it, it was only 100 years ago that it would take you months to get there, right? And now we're talking seconds, right?
Right. If I wanted to send a letter to somebody there, right, it could take months. And now you're like, 15 seconds is so long. Okay, so just a couple topics left. And then we're almost at the end. So different kinds of joins. So just to understand, so you can do stream joins where basically, typically, they're both going to be windowed, and the key idea here is that you need to preserve some type of state, right? So typically you're talking about some kind of hash index on join keys. And so you're going to keep that. If you have two streams that you're joining, you're going to keep that on both of them, and then you're going to look up hash indexes in order to match the things from two different streams. And so the example in the book is a stream of clicks and a stream of searches and a stream of clicks, and the clicks will be a subset of the searches. You can have stream table joins. And again, like whether you think of these as fundamentally different or not, I mean, that's up to you. But in terms of implementation, if you know that this is the kind of join you have, then essentially your hash table for the table part of it is going to be a complete copy of the table. It's not going to be this windowed thing. You're just going to have the stream from the beginning of time to current, all saved, the most up to date. And then finally, the table join. There's different ways you can think of it, but essentially, if you imagine just a like a SQL query, a join, giving the information of A joined to B, and then I'm going to present that as a view, A join B. Well, then if you have streams that modify A, then anytime that updates, then it's going to potentially affect multiple rows where it matches on different things from B. And anytime something changes from B, you're going to have multiple rows that it matches from A. And so that's when you get this idea of basically a stream constantly refreshing materialized view of the join between those two tables. And then I don't know if you guys read it, but I actually thought it was really cool, the little footnote that talked about the calculus rule for the derivative of products. So the derivative of u times v is udv plus vdu.
Yep, saw that. Yeah.
Yeah, I thought it's like, oh yeah. So if you want to have streams maintaining the join between A and B, you need to know all the changes to A, you need to know all the changes to B, and you combine the two. All right. Finally, when it comes to fault tolerance, so it's great you're doing all this streaming stuff, but what happens if a machine goes down, right? So typically you're going to see microbatching or checkpointing, which means that periodically you need to write to durable storage your information. Typically you're not going to get atomic commit, but I guess between streams you can get a sort of smaller version of atomic commit. You can use idempotence, and so there's true idempotence. All right. So if you say set x to 3, you can run x equals 3 millions of times and it'll still be 3. Whereas if you say increment x, you better not run it multiple times because you're going to get a very different result. And then they also talk about, well, if you have sort of this idea of this, like, auto incrementing counter or whatever, then even if the operation itself, like increment, isn't truly itself idempotent, if you're just smart enough to know, oh wait, you told me to do this again, but I know I already did that, then you can basically be smart enough not to repeat things, and so you can give the appearance of idempotence even for operations that aren't themselves actually idempotence. And so if you do that, then you don't have to worry about some of this stuff where you just basically you can retry and you don't have to worry about it affecting the value. But ultimately, you do have to handle the condition where some node goes down, and then you have to basically rebuild the state before you can start processing new messages again. And that's why you use a system like, again, I apologize, I'm familiar with Spark streaming, and so That's why you use something like Spark, because it actually manages that overhead for you. And if a node goes down, it rebuilds all that state. You don't have to write any of that code. So, so that's the benefit of having, for streaming analytics, that's the benefit of having something like that. And so then ultimately, your message broker's implementing, stuff again, to abstract it away so that you don't have to deal with it. So to wrap up, right, we have streams where we have continuous data. There's two styles. This AMQP JMS style is basically where as soon as the message is delivered, you can delete it. You're not persisting it. And generally speaking, you want log-based message brokers because you actually like some of the additional functionality they can give you, because they maintain stuff on disk. You can integrate all kinds of systems, heterogeneous systems, different vendors, different whatever. There was the author's note about, it may be useful to think that just because historically people have read and written from the same database, maybe you don't want to do that. Maybe you want to actually have one system where you're writing information and a different system that might store information a different way for you to read information, possibly multiple different informations where you read information. And then finally, we talked a little bit, not a lot of gory detail if you're going to actually code something like Spark, but we talked a little bit about the windowing strategies and the joins that are necessary behind the scenes in order to do stream processing, because at the end of the day, you're almost never going to be lucky enough that all the information you want is always just in one stream. You're going to have to merge that stream data with data from somewhere else. So that's our chapter. That's chapter 11, streaming. Anybody else have any comments, what they thought about the chapter or anything else before we wrap up?
So for me, kind of what you said at the beginning, which is I wish that there was a little bit more practical advice in there. I mean, this is all really great theoretical constructs to understand, and I'd certainly learned a couple of things, but I wish it was a little bit more practical about that. And so having said that, I was just going to throw it out to the group. I mean, have people figured out a way to do sort of the atomic commits, or is it just eventual consistency where eventually the consumers will read stuff from the streams and make sure that, when the patient comes in, their deductible gets decremented and their, the visit gets documented and blah, 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 but it's more eventual consistency that rather than atomic consistency, right? Or atomic commits.
I don't know. Does anybody have a comment about that? My high level experience is that, you're using something like Kafka or Kinesis, that it gives you this guaranteed delivery and this exact once delivery, which is wonderful, but it's eventual. So if stuff is crashing, stuff's going down, all bets are off. You don't know when stuff's going to show up. So like you said, in the world where you're decrementing from one system and adding to the other one, yeah, if one of them goes down, you could see the decrement and you don't actually see the other one happening. That's just life.
Yeah. And it's probably good enough for most situations. I was just curious if anyone has any experience with something more concurrent.
Yeah, I agree with what Stevens. I don't have an answer to your question, but that this chapter has a lot of technical details, but like what I did with Kafka is more like, I start taking messages and do all the downstream joining the tables. I think it would help put the case forward if there is more like code examples like, this is what is actually running in an actual application. Yeah. But I mean, I appreciate all the details, though, but it's not what I actually, it doesn't have any tips to help me to improve writing an unbreakable application.
Yeah, I think that this chapter is completely consistent with every other chapter in the book in that it's high level, it's conceptual, there's no code examples. But as we get later in the book and as we get to more like higher application level concepts, for me, it's a lot more real, right? I'm not building a replicated database, so I don't really worry about code examples. I'm not writing a competitor to Cassandra, you know what I mean? So I didn't worry about it when we were reading chapter 5. But now it's like to the point where, oh, this is actually stuff that I can do a little bit. And so I was, so I think the chapters are the same. It's just my expectation changed when I got here. I was hoping, right? But so I
Yeah.
think it's fair to say that the chapter's consistent with the rest, and I guess you just need to read a whole book dedicated to streaming if that's what you want.
Or we write some example for them and ask them to include that and list us as authors.
Well, there you go. Yeah. I don't remember seeing this. Well, they have the updated references that are being maintained, but I didn't see any other addenda like hey, here's some code examples, here's some notebooks that talk about these concepts.
Well, it sounds more like we're proposing a companion book, right?
Yeah, I haven't read many, but I'm sure there are lots of books on like Kafka.
Well, the other thing to keep in mind.
Practical guide to data intensive application.
Exactly, right.
There
The
you
other
go.
thing to keep in mind is, remember, this guy wrote this back in what, 2015, I think it was, right? So he's done an excellent job, given that a lot of the stuff has actually evolved quite a bit since then.
Yeah. If you think about it, some of this stuff was more cutting edge when he wrote about it. I think was it copyright 2017, but yeah, it's pretty amazing given the way technology is going that this book hasn't aged more than it has. It hasn't aged that much. All right. Any other?
It's so high level, right?
Yeah. But still, it's not like, oh, by the way, that chapter is obsolete because now we have this way of doing replication. Nobody's like come up with some breakthrough algorithm that just makes something in this book out of date. Cool. Any other comments or questions? We're past 1:30, so happy to wrap this up and move on to the project meetup. All right. Well, thanks everyone. Appreciate you joining us. And Ryan, I don't know if you peeked at all at the last chapter of the book.
I haven't looked yet.
So next week's the last chapter. I haven't really read it, but I did peek it, and it just looks like it's organized very different. So I'm not quite sure how that content is going to go.
Well, the other thing I noticed is it's a little bit long on the longer side as well. I think it's like 54 pages or something like that. So there's a little bit more to it.
A lot of these recent chapters have been longer than the beginning of the book.
Yes, I noticed.
This one was like 50 pages, and I was grinding, and I'll just say I was up late last night finishing the notes.
Yeah, I figured that might have been the case.
The
Hey, have we thought about what the next book is going to be? Speaking of books, and speaking that we're getting to the end of this one.
So Ryan and I have had some discussions. Ryan, I don't know if you want to comment on any of the things that you've been thinking about.
I've kind of floated a few different ideas. One of the things that we've talking a little bit about is some sort of reinforcement learning thing going along with the Sutton book, but just kind of focusing in on some certain concepts, and then we can actually do code examples, and we can say, here, we trained an agent to play Pong or something like that, and it can be a little bit more hands-on, because I feel like this one was a little bit removed. It's kind of hard to actually engage in. But then we were also discussing doing sort of a like just state-of-the-art review or something like that for a couple different categories. So we look at image, we look at text, we look at tabular, and we just kind of go through and we say, here's the stuff that's happened in the past here. Here's what the current state of the art is. And it could be something that we do either annually or something like that. And we just go across the few different categories and we can just kind of talk about what's new, whatever the hot stuff is.
Both are great. I mean, I'll volunteer myself. If you guys decide we want to read a book on reinforcement learning, then one of the things that I had proposed months ago was maybe delving into and setting up our own little team for AWS Racer, which uses reinforcement learning. And that would be kind of cool, right? A cool kind of companion to what we would be reading at the same time. So I'll volunteer myself for that if we go down that path.
Thanks, Steve. Yeah, I mean, honestly, one of the things I talked about, we commented a little bit earlier, right? So this is chapter 11. It's a 12 chapter book. I think most people don't necessarily want a, double-digit length series on a particular topic. So I talked to Ryan about, so I mentioned reading the Sutton book, right? So instead of doing the Sutton book chapter by chapter, what if we just picked 3-4 things and we did 3-4 weeks about reinforcement learning instead of going through the whole thing. So possibly just sort of tweaking the approach a little bit to be less, chapter by chapter, blow by blow.
Okay.
Time to move on to products.
Yeah, I think so.